Thank you for the introduction. Here again, last talk, responsibility. We are going to talk about power integrity. Power integrity is a problem typically for digital designers. No, they are worried about the possibility to have problems with the difference between the 0 and the 1 because the signal is distorted when you don't have the possibility to have a good power supply in your system. So the design of the power distribution network in a PCB is a complex subject to be able to be sure that all the components in the PCB are receiving a good voltage, constant, and without a lot of ripple, blah, blah, blah. No? So this is the idea of the problem, no? This is of the ideal world. Remember that we are not interested in signal integrity. We are going to analyze how this effect has a strong influence in EMI. So this is the idea. You have a component, consider digital, but perhaps could be power electronics, or this could be audio or something like that. The idea is that at the input system, or the input connector, you have some kind of ideal voltage. This is from a Thevenin point of view. It's something like this. It's an ideal voltage source in continuous value. No, what means it's an ideal source? There is no output impedance. If you put any kind of load at the terminals, independently of the current you are consuming, the voltage is V, no change. And you are expecting between the VCC and the ground terminals in this component, or in this set of components, you are expecting VDC. You are switching. Every time you are switching, you are carrying current in this line, and this transient, this activity is returning through the ground system. This is the ideal result. So this is my schematic. This is ideal. This is your schematic. What is what you try to implement in your circuit? This is what you want to implement. But this is the reality. Okay, so this is the same with your circuits. You have one schematic, it's a drawing. You have something that you want to implement, and at the end, what you are implementing is not this ideal response. Let's see the problem. This is a typical picture. What happened if we model the system in this way? We have a voltage source, this one. You have a load that is taking current. He needs transients of current. If this is a radio frequency transmitter, you need transients every time the power amplifier is switching or is amplifying. If this is a digital circuit, you have transients every time the transistors are going on to off, off to on. No? And what is between the power supply and the device? You have impedance. Let's consider that we have resistive and inductive values. This is related with what? This is related with the bond wires in the integrated circuits. This is related with the traces and how you are doing the layout. This is related with the output impedance of your voltage regulator. Remember, the voltage regulator is trying to fix a constant voltage, but usually it's working only at low frequencies. For frequencies below 1 kilohertz, no? The voltage regulator cannot change the voltage as fast as you are trying to take current from the power supply system. So what happened with the resistive part? You have in this current, you have some kind of DC activity, you will have a voltage drop, DC voltage drop. This is not typically a problem. The problem here is that this current has some kind of transients. That means what? You have DIDT. This is what is dangerous. If you mix DIDT with inductive effects, you will create a voltage drop. So at the end, you have in your component a voltage drop that is proportional to LDIDT. High inductance, high DIDT, high voltage drop. So in digital electronics, for example, you are in 3-5 volts, something like that. Typically, you will not desire more than 5% of ripple in your power supply system. This is a typical limit, no? So you don't want a voltage drop more than 5%. If the voltage drop is limited to 5% of VDC, you need to limit the L value, the inductive value, for some specific DIDT. No? This is the problem with signal integrity. Every time the system is switching, you will have some distortion in the power supply values. No, this is the voltage in the integrated circuit. This is the voltage in the integrated circuit, and it's not constant. Because the voltage is not constant, the signal of your clock or your digital signal is distorted. Signal integrity. But what about EMI? In EMI, the current is taking this path. So you have different problems. The first problem is that the current is going through some kind of loop. This loop can radiate? Perhaps yes, but probably in a PCB, the loop is so small that you will not have a good antenna for radiated emissions. If you are going over gigahertz, over 1 gigahertz, perhaps the loop in the PCB with a bad layout, without ground planes, can radiate to external system. But if you have some kind of loop, additionally to the radiation problem, you are creating magnetic field, and you can create problems related with crosstalk. Other loops, other signals, sorry, other signals in the same PCB will pick up these transients, no? But what is more important is that if this activity, these high frequency transients are taking this path, the idea is that they go to the connector in the power supply system. And they, in this situation, you have access to the cables. And if you have access to the cables, the activity of your switching components will be seen in the far field. The antenna will be the cable, but the origin of the problem is in the integrated circuit. So how is the solution for this problem? The solution for this problem is to put a component close to the integrated circuit, typically a capacitor, because a capacitor is an open circuit for DC, it's invisible for the DC signals, and it's a source circuit for AC signals. So what happened? The activity in the line with the same impedance here, the activity here is only DC. If the activity is only DC, that means the transients that are AC are coming from the capacitor. So depending on the component you are decoupling, it's not the same audio, power electronics, digital electronics, you will need a big capacitor for big transients, but additionally you will need a broad frequency response if you have energy in very high frequencies, hundreds of megahertz. So you need to identify how many capacitors, what technologies, where you put the capacitors, what about the parasitics in the layout, no? So the idea is that doing this, the loop that was dangerous previously now is a very small loop if you do things in a good way. The activity from the EMI point of view is not in the connectors or is not spread at the PCB, is concentrated around the component. Then this is what we are going to analyze today. No, you know, or you can read, of course, if previously the voltage changes were in this way, now the voltage in the component, in the block you are decoupling, will be close to constant. So the signal integrity is recovered. This is the idea, no? But I am not interested in signal integrity. I am interested in EMI. And from the EMI point of view, what is very important is that the energy is in a very small part of your PCB, out from the connectors, out from sensitive areas. If you don't do the decoupling in a good way, forget signal integrity, you will have the energy spread around the PCB. It's impossible to control this energy. You will not be able to filter. You will not be able to reconduct the energy to other areas because it's in a multi-layer PCB and it's very complex to control. So at the end, you will need to add filters in the cable, or you will need to seal the full product in some way. Okay, so you will have a lot of articles and books explaining where you put these components. You know that the component must be very close to the integrated circuit with short traces, very wide traces, and of course, with vias connecting to the power supply and GND planes. No, I'm not going to cover these ideas here. It's impossible in the time we have. But for example, if you have a capacitor that is doing this work, you will take the decision to connect the capacitor to the ground and the VCC planes or traces with vias, no? And you know that if you do this connection, if this capacitor is connected to the VCC plane with a via here and a via here, this is not a good connection. They are very far from the component. You will have bigger loop and the decoupling will not so effective, no? You know that it's better to put the vias close to the component, something like this. But if you read books, you will see that it's better to put the vias in this position, no? So minimizing the length of the connection to the ground plane and the VCC plane, you minimize the loop. That means you minimize the inductance. The important part of this work is not where is the inductive value of the capacitor, the self-resonant frequency of the capacitor, because this is the inductance you consider when you are modeling the capacitor. I don't know, in 1206 package or 0805 package, you have around 1 nanohenry, 1.2 nanohenries of inductance. This is not the inductance that is important. This is part of the inductance that is important. But the important thing is how is the loop where this capacitor is introduced. If the loop is small, the total inductance, not the partial inductance, will be minimum. And with a minimum inductance, there will not be, or you will have less problems, no? Okay, so considering this idea, we have the possibility to introduce more than one capacitor. And how is the idea? This is what we want. If you have a circuit that needs to be decoupled, when you have transients at some frequency range, the idea is that from the theoretical Thevenin equivalent of the power supply, the output impedance, this is the impedance of the power decoupling network or the power distribution network, you can call as you prefer. No, this impedance must be ideally zero. If this impedance is zero, that means that the current must be as high as you want, but there is no voltage drop. This is impossible. This impedance is the result of this analysis. If you are the integrated circuit and you look in that direction, you see what? You see the impedance related with the layout, with the bond wires, with several capacitors, with the inductance of the capacitors, with the inductance of the layout, your traces. You have the capacitance between the planes, you have VCC and ground planes, and additionally, you have the output impedance of your voltage regulator. The result of these impedances, if you go from here to here with circuit theory, if you calculate the equivalent, you will see that the impedance is something like this. It's small in some frequencies, high in other frequencies, and importantly, we have resonances. If you have energy in your current that is in this area, you are not decoupling this energy. And these harmonics, this energy is spread around the PCB. And you know, Murphy, where is your energy? Where you have these peaks. This is the problem. So if you study the analysis of decoupling networks, you will see that many designers have the proposal of using a target impedance. You need to convert this, I don't know, multiple resonance behavior in a low value for a high frequency range. And this is not easy. You cannot do this with one capacitor. Remember the 100 nanofarad capacitor that all the people put between VCC and ground, no? This is today, you cannot have decoupling with only one capacitor. You need several capacitors. In general, a lot of capacitors, because the trick in the high frequency range is to minimize the inductance, not the capacitor. And to minimize the inductance, you need to put a lot of capacitors in parallel. And in general, remember the sentence in EMI depends, it depends. In general, the capacitor must be in the same value, equal, not different more than 1 decade. Because if you put different values of capacitors in parallel, the problem is that the response will be something like you see in the green color. You have low impedance in some range, but in some specific frequency, you will see this peak. Why? Because you have different capacitors in different technologies and packages. The big capacitors, electrolytic, will have a high inductance. The very small capacitors, SMD, you will have a high self-resonant frequency and the inductance is lower. But in some part of the frequency range, some of the capacitors are inductive and the smaller capacitor is capacitive. So what happened at this frequency? You have an inductive effect in parallel with a capacitive effect. And the resonant frequency of L and C in parallel is what? It's an open circuit, it's a high impedance. You can try to solve the problem introducing some impedance between the elements that are resonating, ferrite, a resistor, so you try to damp the peak. But some people don't like to introduce impedance in the VCC line, no? Is good or is bad? I don't know. In my experience, I have not experimented problems introducing this small ferrite bead. But if you go to a symposium, this is something like I usually do. I go to a guru in EMI or signal integrity and I ask, can you give me your opinion about introducing the impedance in the path? And he says, for example, never do that. You take the coffee, he explained very kindly. And of course, the reasons are reasonable. But you go with other coffee to another guru and you say, what do you think about introducing? Do this always. So you go out of the symposium and you don't know about. This is something like the question about a ground plane below the inductor in the buck converter, or about connecting in some way grounds in one point or different point. No, they are topics that are difficult to answer. No, but the idea is that you need to measure these. You can measure this with a network analyzer in your PC board, so you can identify you have these kind of peaks. So let's show this with a demo. In my demo, I am going to use this board. No, let's go to the PCB section. This is my product. It's the same box. Inside of the box, I have a power supply and I have a digital circuit. Let's connect the antenna. I am using the antenna to measure radiated emissions. So let's go to the screen of the oscilloscope. Now the system is on. Let's activate the FFT. This is the signal from the antenna. And let's put the frequency range from DC to 300 megahertz. Oh, sorry, to 300 megahertz. And with a resolution value of 100 kilohertz. Okay, something like this. It's disconnected, sorry. Now this is, oh, sorry, wait a moment. This one. Okay, this is ambient noise. Let me increase the intensity of the signal. Let's see here, persistence, signal. Okay, so you can see better. This is with my device on, off, and then I switch on my device. You can see that I have a strong emission here that is broadband. This is from my buck converter. But additionally, let me increase the amplitude so you see better. Additionally, you can see peaks, peak, 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 peak. This is coming from where? From my digital system. And it's radiating. Why? Because I have a long cable, the power supply cable. So the activity from the buck converter is going to the cable and is being radiated in this frequency range. And additionally, the activity from my digital circuit is going to the power supply cable and is radiated by the cable. I am not interested in the buck converter. So let me open the box. Let me disconnect the digital circuit. And I am working only with the digital circuit. And I am going to power with a 5 volts power source. So we can go. Let me switch off the DC-DC converter, and let me switch to the camera. Okay, this is my PC board, and this is what I get in emissions. You see that now I have less activity, broadband, because the back converter is off. I have a power adapter, so I have some kind of broadband emission that is lower, and you can see the peak. Consider that this is the peak that is important for me. I am over the limits in that peak, no? So let's go to the FFT menu, and we are going to activate here in the FFT setup the peak list. Okay, and let me change the value where we detect peaks. Oh, sorry, this one. So you can see that the peak is 144 megahertz. If I use a very small resolution bandwidth, you will see that is 144.0000000 megahertz. It's coming from some kind of a digital circuit, no? This is the peak that you are failing in radiated emissions. The other peaks are not important, perhaps because in high frequencies, there is no enough energy, or perhaps in the low frequencies, there is no a good antenna to radiate. My problem is this. So let's go to the FFT menu, and let's switch this. This is 144, so let's change the frequency range from 140 to 150 megahertz. So we put the peak close to the center of the screen. And let me increase, let me see in a better way here, okay, the peak. And we can reduce more the frequency range. We can go from, for example, let's go from, in the FFT, I'm going to unselect the peak list. And now I am going to establish a resolution bandwidth, a start frequency of 142 to 146. I'm not going to reduce the resolution bandwidth. And let me activate the average. Let me see how I can activate the average. Okay, let's see in this way. I don't want to lose time. Okay, so I'm not going to reduce the resolution bandwidth, but if we reduce the resolution bandwidth, we see a peak here, no? Instead of this mountain, that is the response of my resolution filter. Okay, so let's save in memory this. Oh no, before saving in memory this, we are going to measure the current in the cable. No, remember from yesterday, my problem is not differential mode currents. My problem is common mode currents. So you open the current probe and you go here to measure how is the common mode current in your circuit. This is what I am doing. Okay, let me put here. Okay, something like this. You see the current probe and you see the power supply cable. So we activate channel number 2, is where I have the current in the cable. And let me activate the FFT for this signal. From 100, let me show you FFT. So we are going from, I don't remember exactly, but it's around FFT from 100, I think it was 140, no? I don't remember exactly, 140 to 100, do you remember? 146, no? Something like that. It's not very critical now, 100 kilohertz in resolution bandwidth. Let me see if we see the peak. Here is the peak, okay? So in the cable, I have the same energy, the same frequency, sorry, that in the antenna. If you are failing 20 dBs with this signal, then you try to reduce this 20 dBs. So let's remove this time domain signal. Let me remove this time domain signal, and let me reduce the antenna signal, and let me see, this is my interest. Let me save in memory. Ref, we go to the math number 2, and we update, and then in white color, we have the solution without filtering, without trying to solve the problem. How was the solution yesterday for a similar problem with the back converter? It was a broadband emission. but we can try a ferrite, no? So let's go to the camera, and we are going to introduce here a ferrite. Let's see what happened in the oscilloscope. Oh no, you see, no, in the oscilloscope is this. You see, it's around, I don't know, 10 dBs. Let me save in memory. Reference number 2, I activate. Format number 2, update. Oops, no, sorry. This is a mistake. Reference 2 is format number 2. What is wrong here? Why is in the center? Oh, why is not? No. What happened? Sorry. So this is with ferrite. Let me save in memory. In reference 1, update. Okay. So this is with ferrite. Let me remove the ferrite. And then we have this. And then I save again. Reference. Now in reference 2, Matthew, update. I don't know why it's in the center, but this, you can see the difference, no? This is with ferrite, this is without the ferrite. So I am reducing 10 dBs, 8 dBs. This is the typical result with ferrites. Let me open the circuit, or let me show you with the camera the circuit. This one. This is the PC board, and this is the schematic. You see, I have a digital circuit here. The output of this digital circuit is a square wave clock. I am not interested in the square wave clock. I am interested in the power supply network. In the power supply network, I have a 5 volts line powering the device, and I have a return path with 2 possibilities. We have the possibility of a big loop in the PCB, or I have the possibility of a small loop with a trace that is very close to the first one. No, you have VCC and ground. The best option would be VCC and ground plane, but in this PC board, I have different possibilities for different experiments. How I select one path or other with jumpers in the PCB. I am going to use the big loop. This is the board. Layer 1 is red color. Layer 2 is blue color. So this is the VCC line. This is 5 volts. And this is the ground line, something like this. So what I have is transients going in this direction. Sorry, this one is transients are going in this direction and are returning in this direction. There is no decoupling circuit. Look at this. The decoupling circuit is done with this. It's a capacitor and a ferrite in series, something like this. Ferrite and capacitor. But the ferrite and the capacitor have 2 jumpers. So I can introduce or remove the decoupling circuit easily. It's very bad situation because the jumpers introduce a lot of inductance. But for the demo, it's the best option. Now there is no decoupling network. Let me show you what happened in the measurements when I introduce the decoupling circuit. So now is without the decoupling network system. Remember, the left line is with the ferrite. The green line is the original situation. And now I am going to introduce the decoupling network. Okay. You can see that the reduction is more than without the ferrite. I am using only one capacitor, and there is a lot of parasitics. So if you try to see this with your scanner, how is the result of this exercise? It's something like this. You see, oh, sorry, something like this. This is the power supply here, input. This is the USB connector. Here is the component for the clock. Here is the ferrite bit. Here is the capacitor close to the integrated circuit. You see here the VCC line, and you see here is not here because it's in the other side of the PCB, is the ground line. No? So I have this loop. You can see in red color where we have a strong magnetic field. Why? Because the magnetic field is close to the areas where you have current. So you have a quiet area where you have a loop and you have current. Where is the quiet area? In the center of the loop. The center of the loop is not presenting magnetic field. The magnetic field is close to the conductors where you have the current. So what is interesting here about EMI? I have a big loop. This big loop is creating a lot of problems. For example, coupling the energy to slots or other circuits. But look at this. This is red and green colors. So what happened? The energy is able to go to the cable, and you can excite the cable in common mode with some kind of coupling. We are not going to explain that complex problem now. The important thing is when you introduce the decoupling system, what happened? How do you think that this will change with the decoupling circuit? Where will be the energy? The energy, instead of around the PCB, creating crosstalk, creating radiation, creating common mode impedance in sensitive traces in this ground system, instead of the energy in this area, will be around the element that is angry of the transients. So this is the result in the same scale. Okay, the energy is concentrated. You are controlling the energy, and this is very important for EMI. So the coupling networks, the power distribution network, is something that is very important for digital electronics designers. They are worried about signal integrity. Let me see, how is the signal integrity of my circuit? Let me make a preset of the oscilloscope. We are good on time? We are on time? Okay. How much we have now? 15 minutes more? Okay, thank you. Okay, let me show you how is the signal. The first thing to do is to look at the square wave signal, something like this. Let me show you what I see with the camera. This is what I am doing. Okay, you can see here, and let me switch on this one. I'm going to show you something very interesting. Okay. Okay, this way. So this is what I have here. Let me show you in the camera. And this is the result in the screen of the oscilloscope. It's a 24 megahertz clock, more or less. I don't remember exactly the frequency, no? But there is a problem in my setup, no? Because I am doing this. Let me take a picture. Okay, let me take a picture here, so it's better. We add a new set, and this is technology, so we can use technology for us. Let me take this one. We go here again, and we connect. So, yes, picture, this one. Okay, let me switch to the iPad. So this is the signal we want to measure. Let me go talk VS. This is a signal you send to the oscilloscope, VO. And you have two effects. VO is equal to VS plus 2 additional voltages. One of the voltages is created by this inductance. This is around 120, 100 nanohenries. So what happened? This is your signal, VS. This is the inductance of the pigtail, and this is the input capacitance of the probe. So what you have what? You have a underdamped system. So when you have a square wave signal, the output of this element is ringing. So the ringing is not from my signal, it's from the setup. And additionally, we have another problem. We have a loop. And this loop can pick up noise from areas that are around the PCB. So if you put your probes on top of it, some kind of power electronic circuit, this loop will pick up noise. So this loop is related with this voltage, and this voltage is coming from the Faraday law, no? Big loop, more possibilities to pick up. That is because I am going to switch to this situation. You go to the probe, you remove the ground terminal, and you connect without pigtail. Okay, and then we switch to the PC, and we see the difference, no? There is no ringing, be careful about that. But let me show you how is this signal without the decoupling network, when we are radiating a lot. Now we are radiating, and the signal is distorted. Because I am a digital designer, I am worried about the distortion. So let me show you how is the power supply voltage of the clock. I go to channel number 2. I am going to connect to see how is the voltage in the integrated circuit. It's in channel number 2. So let's go to lower amplitude, and let me move this way. Okay. So why is start? No. Sorry, it's doing bad contact. Wait a moment. Now, let me go down with the voltage. You see? Yes. Let me remove this one. This is the voltage in the power supply of my clock. If you move up and down this trace, you will see that the envelope of the output of the integrated circuit is following the changes in the power supply. If we introduce the decoupling network, this is the result. The power supply is constant, and the signal integrity is recovered. And now I am not radiating. At least I am radiating 15 or 20 dBs less than without the decoupling network. So this is the relation in between power integrity and EMI. That's all. I think it's enough, no, for today. Remember, this is the difference.
So thank you very much, Arturo. Do we have any question from the audience here, which we have on site at our MPS location? So we have one question.
Yeah.
This picture, is it from a simulation like CST, or is it a real measurement?
No, it's real measurement.
So
Yes.
a 2D table, and you can put your PCB.
Exactly. Exactly. You can simulate, of course, but this is measurement.
So there's one more question.
Yeah.
Is there further improvement when using a small loop?
In the decoupling?
Can you repeat the
radiation?
question,
No.
please?
Yes, sorry. The question is, what happens if I select in my PCB the small loop? Okay, instead of returning in the big loop, the ground system going very close to the forward path for the current. No differences in the radiation from the cable. Of course, there are a lot of differences because this loop disappeared. So probably you will not have this kind of crosstalk problems or common impedance in the PCB, but you are exciting the cable, so you will fail. Yes.
So there's one more question.
Yes.
You showed the difference after a measure within size. I didn't get it, what the change exactly was.
What was
Yeah, before and after. What did you?
in value?
Yeah. For example.
No, the question is, if I understand very well, the question is how is the difference between introducing or not introducing the decoupling network in the amplitude of the emission? No.
What was the change? This I didn't get.
Sorry, I don't understand the question.
The change in that circuit.
Ah, the change I am doing. Oh, okay. This is what I am doing in the schematic. In the schematic, perhaps we can draw it. The question is what I am doing in the circuit to obtain the differences, no? So let's draw this with jumpers. This is the idea. So this is my integrated circuit. This is my ferrite. This is my decoupling capacitor. And then I have here two jumpers. So when I short circuit the ferrite and I remove the jumper in the capacitor, there is no decoupling. When I remove the jumper in the ferrite and I connect the jumper in the capacitor, I have this filtering decoupling network. That's all. And this ferrite is that some people will recommend no to introduce. Okay, so my recommendation is to test in your application. More?
So one last question from the online audience. Which scope did you use for the measurements and what options were needed for the software/firmware? And was the R&S current probe also plugged in the scope on a 50 ohm setting or an EMI receiver?
No, it's an oscilloscope. It's from Rodan Schwartz. It's an RTO. There is an RTO6, but basically you can go to any family. This is RTO6 from Rodan Schwartz, but you can go to other families, RTM, RTE. The RTO6 is a high level oscilloscope. And but the lower in the family instruments are similar because the FFT is coming with the instrument, and you will be able to do the same works. And the probe is connected. The current probe is connected to channel number 2 with a 50 ohms input impedance to avoid reflections. No?